All right, this is a lecture where I'm going to review statistical inference. This sometimes I feel like, oh, is this lecture even necessary? But then I think it is. In the past, um, I know Stats 10 or AP Stats or Stats 15 or some kind of intro stats class is required as a prerequisite, but but I'm not sure if everybody has the same kind of foundation. So in this lecture, I'm going to try to compress all of intro stats, at least the statistical inference, into just kind of this one lecture. So it's it'll be a little bit quick, a little bit all over the place, but also I think it's a good review. So so let's get into it, okay? So first, I just want to start off with like what the mean and the median are. Obviously, you guys know what these things are, but I want to just kind of conceptually make sure we understand what these things do. So these are both measures of center, okay? And the key idea here is the median balances the number of points that are lower or higher. All right, so the median balances the number of points, so you're going to have the same number of points below the median as you have number of points above the median. Whereas the mean balances the deviations of the points that are lower or higher. So when you look at the mean and you measure all of the kind of the distances from the mean that are below and the distances from the mean that are above, they all balance each other out, okay? And therefore, the mean gets pulled by outliers. So when you have an outlier that's extremely high, because the mean is trying to balance those distances, the mean gets pulled in the direction of the skew, okay? The calculation of the mean, you add them up and you divide by how many you have. That's kind of just like this neat little coincidence or neat little way of getting this thing that's going to balance out all of the deviations. But the mean balances the deviations. So the mean gets pulled in the direction of the skew. In general, if we have a skew distribution so that you're using a value that's not affected by it, the median is preferred for these skewed distributions. So here's kind of an illustration. Let's say I have these numbers, 1, 2, 3, 4, 10, and 10, okay? The median is going to be at 3.5. Between 3 and 4, you're going to have 3 values below the median, 3 values above the median, the 4, 10, and the 10 above the median, okay? Whereas the mean is going to be at 5, okay? Because at 5, here I've plotted out the points, 1, 2, 3, 4, and 10, and we're measuring the deviations from the mean. So 10 is 5 above the mean, and this 10 is 5 above the mean, okay? Whereas the values 4 is 1 below the mean, 3 is 2 below the mean, 2 is 3 below the mean, and 1 is 4 below the mean. So if you take the deviations below the mean, they add up to negative 10. The deviations above the mean add up to positive 10. And therefore, you got positive 10 and negative 10. They balance each other out. But you can see how having these kind of two values that are much higher than everyone else pulls the mean in the direction of kind of the skew there. We have variance and standard deviation. These are values that, summary values that measure the spread of the values. Smaller values of variance and standard deviation mean that the values are closer together. Larger values of variance and standard deviation mean that the values in your data are more spread out. So examples I like to use are, imagine the ages of students in a second grade classroom. Pretty much in that second grade classroom, everybody has the same age. They're all like 7 years old or 8 years old. And therefore, the variance is very small variance, just because almost all of the data values that you're going to get in that second grade classroom, pretty much the same number, okay? Meanwhile, imagine going to, say, the DMV or a doctor's office or something, where you have a whole bunch of people, and in that room, everybody's ages are all over the place, right? You've got older people, you've got younger people, so you've got, teenagers, you've got young adults, middle-aged people, older people, seniors, babies of people. So everyone's got all kinds of ages, you're going to have large variance there. Okay, we can think of the variance as the average squared deviation from the mean, and then the standard deviation would be the square root of the variance. So kind of going back to this side, here's these orange lines are the deviations from the mean, and if you square all of these things, you'd get your squared deviations, and then if you take the average all of them, that would be your variance. Okay, so if you take all of the deviations from the mean, you square them, and then you take the average, that's going to be your variance. When you're taking the variance of a sample, you apply Bessel's correction and you divide by n-1, but that's beyond the scope of the course. That's mathematical statistics. But one thing about squaring the deviations is that values that are far away, like outliers, kind of have an outsized impact on the variation, okay? Because if you have 10 values that are 1 unit away versus one value that's 10 units away, the 10 values that are 1 unit away, when you square them up and add them up, you get 1 squared times 10, and you get a total of 10 for your squared deviations. Whereas if you have one value that's 10 units away and you square that, you're going to get 100. Okay, so squared deviations are much more affected by outliers. And you can think of the variance as kind of the average of the squared deviations, and the standard deviation is a square root of the variance. But again, they're all the squaring has a outsized effect on larger deviations. Okay, the formula for the variance is done this way. Okay, so you get your distances from the mean, you get your squared distances from the mean, and then you can add them up and divide by n. That would be your average squared distance from the mean. This would be how you would calculate the variance if you have the entire population. Okay, but if you don't have the entire population and you're just dealing with the sample mean, then you want to apply a correction and divide by n-1. Again, that's Bessel's correction. And the reason why, it's kind of, again, beyond the scope of the course, but the reason why is because you're using your sample mean, x bar, instead of the population mean. If you knew the population mean, you could just do, hey, what's the distance from everybody to the population mean? Square that, add them up, take the average. That value would not be biased if you knew what the population mean is. But the problem arises when you are substituting mu in with the sample mean x bar. X bar is always going to be like the middle of your sample of values. And so the distance to x bar is always going to be a little bit less than the distance to the actual population mean mu. And so you have to compensate for that. And it turns out that dividing by n-1 instead of n is the exact compensation factor you need. Bessel's correction, you can look it up on Wikipedia. Another key idea in your intro stats class is the normal distribution. The normal distribution is unimodal and symmetric. If data follow the normal distribution, then that means most of the values are near the middle. The density curve is tallest in the center. As you get higher above, it goes down, and when you're above 3, it's very close to 0. When you're below -3, it's also very close to 0. So, and I think you learned the numbers, right? 95% of values are between 2 and -2. 99.7 are between 3 and -3. And then about 2/3, 68% are between 1 and -1. Those are some good numbers to remember. So these are the empirical rules. 68% are within plus or minus 1 standard deviation of the mean. 95% are within 2, or more accurately 1.96 standard deviations of the mean. And then almost all, but not quite all, 99.7% are within 3 standard deviations of the mean. A key idea is that we are trying to make inferences about populations, but we have to deal with samples. So every research question that's out there has an associated population. The population is everyone who is relevant to answering the research question. That population is going to be too big to be studied directly, and we might not even know how to identify everyone in the population. So, for example, let's say you're interested hey, is some experimental drug, XYZ, is that effective at treating some disease that's out there, disease JKL? Okay, the population there is everybody with disease JKL, but there's no way to kind of track down every single person who has this disease. And even if you did, there's going to probably be too many people for you to kind of study all of them. But yeah, again, no way to track everyone down. Probably a lot of people don't even know they have this disease. And you name any disease out there, you know, some people are going to be aware they have it. And then there's also going to be a bunch of people who, you know, just don't go to the doctor, have no idea that they have this particular disease or genetic condition, things like that. So, how are you going to find these people if they don't even know who they themselves are? So, you know, it's impossible to, in most cases, whatever your population is, it's generally impossible to track every single person down. So what do? We deal with a sample. Okay, we select individuals from the population to be part of our sample, and then we study that sample, and based on what we see in the sample, we then make conclusions about the population. That's statistical inference. So sorry for this ugly diagram, but this giant, I don't know, potato-looking thing, this is supposed to represent the population. It is too big for direct study, and so these dots are individual data points. We select individuals at random to be part of our sample. Okay, ideally, whatever sample we're dealing with, ideally our sample is representative of the population. Now, one method that should produce representative samples is random sampling. Random sampling is not guaranteed to produce representative samples. It's random. But overall, mathematically, when you do random sampling, simple random sampling, you select individuals one at a time, overall, you should get a sample that is representative of the population. Okay. Now, when you take a random sample from the population, you might calculate a statistic about that sample, like the mean of the sample. But because that sampling process is random, your sample mean, or whatever it is going to differ from one random sample to the next. Okay? So I take a random sample and I calculate the mean, I get some number. You take a random sample from the same population, you get different individuals. You calculate your sample mean, you get a slightly different number. Okay? Some of these numbers are going to be more likely, and other numbers are going to be less likely. How do we show that? Okay, that's going to be the sampling distribution. Okay, the distribution of all the possible values of the sample mean from all the possible random samples out there, okay, at least of a given size, is known as the sampling distribution. If we're talking about the sample mean, sampling distribution of the mean. So we can kind of generate a sampling distribution via simulation. We start off with a hypothesized population, and then what we do is, maybe we arbitrarily specify that the population is normal, and then we say it has a mean 0 and a standard deviation 1 or whatever, right? So we can start off with some imaginary population. This one would be like a standard normal population. And then I'm going to draw a random sample from that population. After I draw the random sample, I calculate the mean of that sample. And then I go back and I draw another random sample from the population. And then I calculate the mean of that sample. And I do this again. I draw another random sample, calculate the mean. Draw another random sample, calculate the mean. Over and over and over again, I record every single sample mean I get. Then I look at the distribution of all of those different sample means. Okay? And the central limit theorem says if your sample is large enough, then the sampling distribution of the mean will follow a normal distribution, and it will have a standard deviation of sigma divided by the square root of n. So you see the sample size n is in the denominator. So as your sample size increases, the standard deviation of your sampling distribution, also called the standard error, is going to shrink. As n gets bigger, the standard deviation of the sampling distribution will shrink. Sigma divided by the square root of n. So here's our population. Our population is the standard normal. I've drawn a random sample of, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think 16 values here, okay, in order from least to greatest. Negative 2.21, negative 0.84, negative 0.82, negative 0.63. They're shown as little red tick marks on this thing. And I calculate, okay, what is the mean of all of these tick marks? The mean is 0.092. That's this vertical line here. Let me draw another random sample. Here's another random sample of 16 values. Okay, you can see the red lines have shifted around. Okay, so these 16 values, I got negative 2.31, negative 1.13, negative 1.04, so on and so forth, up to positive 1.98. I calculate the mean of all of these values, and I get 0.096, so slightly different. Here's another sample of 16 randomly selected values. Negative 1.22, negative 1.15, negative 1.13, negative 0.96, so on and so forth. Okay, the mean of these 16 values is negative 0.197. Okay, here's another one. Here's 16 other values. The mean of these 16 values is positive 0.426. This one has a mean of negative 0.176. Here's a mean of 0.083. So, you know, you could just imagine repeating this process, calculating the sample mean over and over and over again, okay? And so here, I ran a loop, okay? I ran a loop. I said, hey, do this 10,000 times, okay? And what I want you to do is I want you to generate 16 values from the standard normal distribution, just randomly. So our norm, give me 16 values. That's going to be my random sample. Calculate the mean of that random sample of 16 values and store it away in this storage place called sample means, position I. And if you do this 10,000 times, okay, what kind of values do we get? Well, first let's just ask for some summary values. So this finishes running. It takes just a few seconds, okay? And now I have 10,000 sample means here. The mean of all of them is very close to 0. I get 0.0015, okay? What's the standard deviation of all of these things, okay? The standard deviation of all 10,000 values is 0.25018, okay? Remember, the population has a standard deviation of 1, and we have a sample size of 16. Well, this aligns because theoretically we should have a standard deviation of, 1/4, 1 divided by the square root of 16. So 1/4, and we get something very close to that, 0.25018, so off by just a tiny bit, okay? I can create a histogram of all of the sample means, and I plot that, and yeah, sure enough, it looks very similar to the normal distribution, okay? I'd say it's very, very much approximately normal. We can see it has a mean of right around 0, standard deviation of around 0.25, and that looks pretty good, okay? Again, here this is based on only 10,000. If I did say 1,000,000, I would get something that looks even more like the normal distribution because, law of large numbers. Here's a QQ plot, and we see, yeah, overall, pretty follows the normal distribution quite closely, right? You got a pretty straight line here. So, so that's the sampling distribution, okay? So now we can start thinking about statistical inference. The central limit theorem establishes that the mean of a random sample comes from a normal distribution centered at mu, the population mean, with a standard deviation of sigma over the square root of n. That thing is also known as the standard error, and as the formula suggests, it shrinks as the sample size increases. Okay, the empirical rule tells us that 95% of the time, a random value drawn from a normal distribution will be within 2 standard deviations of the mean. So, putting those concepts together, this tells me that when I draw a random sample, there's a 95% probability that the mean of my random sample will be within 2 standard deviations of the population mean. Okay, or or 2, sigma over the square root n's of the population mean. And so I can kind of flip that around. So I know that when I draw a random sample, there's a 95% probability it's within 2 standard deviations of the population mean. So this time, if I have a random sample and I don't know what the population mean is, okay, but I do see that my random sample has a mean of x bar, I can flip this around and I can be 95% confident that the population mean is within 2 standard deviations of x bar, right? So the logic is this. If the population mean is at mu, and I draw a random sample, there's a 95% probability it's within 2 standard deviations of the population mean mu, okay? Now, I don't know what the population mean mu is, but here I observe an x bar, a sample mean right here, okay? Well, I can be 95% confident that the population mean mu is within 2 standard deviations of x bar, okay? So that's kind of the foundation of a confidence interval. The only problem is that we don't know what the standard deviation is. Sigma divided by square root of n, that's going to be unknown to us because the idea of a confidence interval is you don't know what the mean of the population is, so you're looking at your sample mean and you're trying to guess where the mean of the population could be. And so if you don't know the mean of the population, you're not going to know the standard deviation of the population. So you don't know what sigma is. So what we do is we try to estimate sigma, and we say, well, I don't know the exact value of the standard deviation of the population, but I do have a sample, and I do know the standard deviation of my sample is S. So we're going to say, all right, my best guess for sigma over the square root of n is just going to be S over the square root of n. And that's fine. It works out, okay? But when you do that, you're introducing extra uncertainty, right? You don't know if your S is too big or your S is too small. Your S over the square root of n, is that bigger than sigma over the square root of n? Is it smaller than sigma over the square root of n? So what we do is we compensate. We use the t distribution instead of the normal distribution, right? So normal distribution, we would have used 1.96. I would have said 95% confident that mu is within 1.96 standard errors of my sample mean. This time I don't know what my standard error is, so I'm going to use a slightly bigger number, maybe 2.1. I'm going to say I'm 95% confident that mu is within 2.1 standard errors of the mean, or maybe 2.3 standard errors, or 1.98 standard errors. So, okay, so something like 1.96, but a little bit bigger. And how much bigger depends on your sample size. If your sample size is huge, then you can pretty much use 1.96 or just something ever so slightly different, 1.962, right? Just a number that's just a tiny bit bigger than 1.96 if you have a huge sample size. Because if you have a huge sample size, your standard deviation estimate is going to be pretty good. The standard deviation based on your sample is going to be pretty good estimate of the standard deviation of the population. Okay. On the other hand, if you have a tiny sample, right, like 5 observations, 7 observations, you're going to have to compensate a lot, okay, like 2.36 or something, right, kind of a much bigger number than 1.96. So how big your sample size plays a role in what t you use, okay. The other way to do statistical inference is with a hypothesis test, okay. In a hypothesis test, we say, let's imagine a hypothetical situation, a hypothetical population with some hypothetical mean and some hypothetical standard deviation. I keep using this word hypothetical, but that's the whole idea of a hypothesis test. You just say, well, what if this is what the world looks like? What if this is where our data is coming from? And in this hypothetical situation, is it possible to get this data, right? And we can say, well, let's do some calculations. We can perform calculations to see how likely such a population could produce a random sample that has the kind of properties of the sample that we currently have observed. And we can do calculations and we get basically a p-value, right? So kind of one of the basic hypothesis tests is the two independent sample t-test, right? And that's going to take a sample from two populations. So you have sample 1 coming from population 1, sample 2 coming from population 2, and we're going to test to see if their respective populations, population 1 and 2, have the same mean or not, okay? In that case, your null hypothesis will state that there's no significant difference between the means of the specified populations, right? And so if that null hypothesis were true, any difference we observe between the means of our two samples is just due to sampling or experimental error. So basically, like when you observe, it's just because of random sample, like we can explain away any differences we see with just random sampling. That's what the null hypothesis is stating, okay? And so we would go about and we'll calculate a p-value. The p-value is the probability of observing our data or something more extreme under the assumption that the null hypothesis is true. Okay, so again, you're imagining this hypothetical scenario where the null hypothesis actually is true, and then you say, all right, if we take this as fact, what is the probability of getting this data? Okay. So yeah, we imagine two hypothetical populations that have the same mean. And so when we take a random sample from each population, in that scenario, we would expect both samples to have sample means that are approximately equal. Okay? Or in other words, we expect the sample means to have a difference of 0. If they're not equal, right, we want to know if the observed difference between our sample means is significantly different from 0. Is x bar 1 minus x bar 2, is that difference significantly different from 0? And we're going to figure this out by finding the p-value. That is, if the two populations had means that were equal, or in other words, if the null hypothesis were true, what is the probability that just kind of from random sampling, we would get two samples where the difference is, what we observed or something more? So let's just some made up numbers here. Population 1 and population 2 have the same mean values, what our null hypothesis states. We write H0, mu1 is equal to mu2. All right, let's say we go out and we collect data. X bar 1 is 10. We have one random sample and the mean is 10. And we take another random sample, right? The mean of that sample is 12.5. Okay, so we're not getting the same numbers, right? The case, now we want to know, okay, I got 12.5 versus 10.0. I have a difference of 2.5 points, okay? Is the difference between these two sample means, is that significant, okay? And, as always, the answer is it depends. And in this case, it depends on what the standard error is, right? So in one scenario, the standard error is very small. And so that difference of 2.5 is like huge compared to the standard error. So if our standard is like 0.5, right? This difference of 2.5, that's kind of a big deal, okay? On the other hand, maybe the standard error is big. Maybe the standard error is like 2, okay? And so this observed difference of 2.5 is not that much larger, maybe 1.2 times the standard error, okay? In that case, this difference of 2.5 points, not significant. So our answer is going to kind of depend on what the data look like, okay? So a p-value. A p-value is the probability of observing our data, in our case a difference of 2.5 points, or something more unusual if we assumed the null hypothesis were true. And what we do is once we get our p-value, we compare that p-value to something called alpha. our significance level. And that's an arbitrarily selected number to decide if our p-value is large or small. Most frequently, we use alpha of 5%, but again, it's an arbitrary choice. You can choose whatever alpha you want. If your p-value is less than alpha, we say our p-value is small, okay? And that means we are unlikely to see these results if the only source of variation is just random chance, okay? But somehow we did see these so-called unlikely results. And so, so again, it would be kind of like, let's say your standard error is like 0.5, okay? If your standard error is 0.5 and you're getting a difference of 2.5, okay, is it possible that just by random chance you get a difference of 2.5 when the standard error is 0.5? It's not impossible, but it's really, 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 really unlikely, okay? Really, really, really unlikely for something like that to happen, okay? And so if that's what we actually got, okay, we did actually see these, quote, unlikely events. And so rather than just kind of presuming that we were just super lucky and somehow got these really wild results, the easier conclusion, okay, is that something other than random chance is responsible for the data we observe. And we would reject the null hypothesis. We'd say, you know what? I don't think that the two populations have the same mean, and I just happened to get two samples that were wildly different, okay? But the easier explanation is to say that, oh no, the two populations actually have different means, and that's why I'm getting two samples where the means are different, okay? On the other hand, let's say your p-value ends up large, okay? You get a difference of 2.5. Your standard error is also quite big, 2. And you go, okay, well, it's not that weird, okay? The p-value is large. It says, yeah, it's not, our data is not unlikely, okay? It's not an unusual circumstance to happen, even if our only source of variation is random chance, okay? Now, this doesn't prove that the null hypothesis is true, but we also can't eliminate the possibility that our data is a result of random chance. So, so we don't reject the null hypothesis, okay? So, in your intro stats class, your hypothesis test probably used the normal distribution and the t-distribution, and those hypothesis tests rely on the underlying mathematics of the central limit theorem, which I think you prove in your Stats 100B mathematical statistics course, right? And that shows that the sampling distribution of the sample mean or sample proportion approaches the normal distribution under certain conditions, okay? What we're going to cover next is a randomization test. And in a randomization test, we test the null hypothesis that there's no difference between group means, okay? A randomization test does not depend on the central limit theorem, but rather it depends on actual randomization, okay? Randomization tests depend on a fundamental assumption of exchangeability, which I will explain when we talk about randomization tests, okay? And but before we get into that, let me talk about data collection and some of the ideas and processes there, okay? So here's a concept review on data collection. All right, so we're going to just use this kind of silly example. So suppose a dentist wants to know if a daily dose of 500 milligrams of vitamin C will result in fewer canker sores in the mouth than taking no vitamin C. So how does, so we want to know, is there a relationship between vitamin C supplements and canker sores? Okay. And I'm going to list out these 4 scenarios. But basically, what you need to pay attention to is, do you have a random sample, okay? And is there random assignment, right? So in this case, scenario 1, okay, we look at all the dental patients in town, and we look at, everybody who has appointments in the first 2 weeks of December. We ask them to be part of our study. And then we ask them, hey, do you take vitamin C or not? Those who normally take vitamin C are put in one group. Those who don't are put in a different group. Then we ask them, about their canker sores in their mouths, and we check their dental records and whatever. And maybe at the end of our study, we observe a difference in the two proportions. Okay? Can we conclude anything? All right. Well, here it's a little bit tough. Okay. Number one, these are not a random sample. Okay. These are everybody with appointments in the first 2 weeks in December. So they are not. They don't represent. They're not really representative of any kind of larger population. So it's difficult to kind of generalize the conclusions to any kind of larger group. All right. Also, this is an observational study. Okay, we didn't assign treatments. We just say, hey, do you take vitamin C or not? And so they're not randomly assigned. We can't draw any kind of cause and effect conclusions because, those who take vitamin C, perhaps they are also more likely to take other supplements. Okay, and perhaps it's the other supplements that are responsible for for the canker sores, right? So maybe a lot of these people take vitamin C as part of a multivitamin, right? And the multivitamin also has vitamin B or whatever. And maybe it's actually vitamin B that's responsible for the reduction in canker sores. We don't know, okay? And so we just know that for these particular patients, those who took vitamin C have fewer canker sores than those who don't. We can't make a cause and effect conclusion, and we don't know if this would be consistent with another group, okay? All right, here, same kind of thing. Patients with appointments in the first 2 weeks, but this time we have random assignment. And we say some of you are going to take vitamin C, others of you are not, where you're not going to take vitamin C, okay? And then we do the study, and then we find that those who took vitamin C have fewer canker sores than those who didn't. What can we conclude here? Okay, so again, not a random sample, so we can't generalize to a larger population. Okay, but this time the treatments were randomly assigned to the subjects. Okay, so assuming all of our other factors are controlled for, then the difference in proportions can be attributed to the vitamin C. Because the general idea here is because we randomly assigned the people to the two groups, there's no rhyme or reason why this group, at the start of our study, we randomly said, hey, randomly put some into group A and randomly put some people into group B. At the start of the study, there's no reason why we would believe group A is going to improve more than group B, okay? Because, as far as we're expecting, we randomly assigned them. Group A and group B should improve at like the same rates, okay? But we tinker with it, right? We say group A, you're going to take vitamin C. Group B, you are not, okay? And now at the end of the study, group A improves and group B didn't, okay? And so we can say, the difference in improvement can be attributed to the fact that this group took vitamin C and this group did not, okay? All right, but we not a random sample, so we don't know if it would be consistent with another group, okay? But we believe we know why for this group the proportion is different. Okay, here we have a random sample, but no random assignment. Okay, so now that we have a random sample, okay, it says we take a random sample of the dental patients in town, convince them to be part of our study. And so here, because the patients were a random sample of dental patients in town, okay, then we can infer that the results observed in the study would be consistent with results from the whole population of all dental patients in the town. Okay, so if we're taking a random sample of dental patients, then we can generalize to the population of all dental patients. Okay, we can't generalize beyond that because, your sample of dental patients will not be representative of everyone else, unless you're confident that your dental patients are representative of the general population. Okay, but that's how we go. Okay, if the dental patients in this town are representative of dental patients in general, we can make this kind of inference. However, we can't make cause and effect conclusions because there was only it was an observational study. It is not no random assignment was done. Okay, so we don't know if it's the vitamin C that causes the reduction or if there's some other confounding variable. Again, there could be other things going on. Okay, and then the last one, we have both a random sample and random assignment. And in this case, you can generalize and you can draw cause and effect conclusions. All right, that's basically what this slide says. Okay. Now, this last scenario of having both random sampling and random assignment is like this happy fantasy scenario. But in reality, it's almost impossible to have this scenario with both random sampling and random assignment. Okay. Experiments require basically patient or participant consent. And as soon as one person declines participation, now you no longer have a random sample. Okay, so it's almost impossible to have random assignment and random sampling at the same time. Now, you might be able to argue and say, the sample of patients you have, the participants you have are representative of the population, and you might be able to point to certain demographic factors and say, like, in our sample, we made sure to get this proportion of, this age group and this proportion of, each gender and this proportion of each racial group or whatever. And you can try to say, our group of participants is representative of the population. Okay. And you might be able to argue it that way, but it's not, again, it's not a random sample. So, but yeah, that's what you have. Okay, let me wrap up this video here, and then we'll take a look at randomization tests next.